In today's session, we are going to discuss advantages of IR spectroscopy. There were conventional methods used for structure elucidation. Now, IR spectroscopy has certain advantages over the conventional methods. We can list few of those. First, very small quantity of sample is required to take an IR spectrum, and even if that small quantity of sample can be recovered back. The time required to record an IR spectrum for a compound is very short. Near about 10 to 15 minutes are enough to record IR spectra of a sample. Once the IR spectra of a pure sample is recorded, it can be kept as a permanent record, and we can have information or the data available for various compounds. And most importantly, when we compare this IR spectroscopy technique with the conventional methods, it is useful for saving chemicals, the time, and solvents. So these are the few advantages of IR spectroscopy. Next, we are going to discuss what is fingerprint region in IR spectrum. Typically, if we look at an IR spectra of any compound, it can be divided into two parts. Yesterday we said the IR frequency ranges from 4000 per centimeter to 650 per centimeter in terms of or in the units of wave number. So these this can be divided into two parts. One region which is on the right hand side from 1400 to 650 per centimeter, and another is 400 to 1400 per centimeter, which is on the left side of the spectrum. What is observed is important. Every organic molecule or compound, it produces a unique pattern in the region of 650 to 1400 centimeter per centimeter. This region comprises large number of bands, and these bands are because of the skeletal and bending and some other type of vibrations. When we look at that region, it is very difficult to interpret those individual bands because it has very complex nature. The bands are overlap on each other, and it is difficult to interpret individual bands. So usually the practice is two samples are compared and we try to establish identity between these two samples. It has been found that no two different molecules have identical spectra. Hence, it is known as fingerprint of a molecule. So, this IR spectrum in the region 650 per centimeter to 1400 per centimeter is known as fingerprint region of that particular organic compound. Now we need to also understand selection rule observed in the IR spectroscopy. We have discussed there are different fundamental modes of vibration for a molecule, which can be calculated by using formulas like 3n minus 5, 3n minus 6. But it has been observed that all the vibrations do not cause absorption of IR radiation. And therefore, the number of bands actually obtained in the IR spectra are usually less than what we predict. So what is the reason behind that? The reason is only vibrations which results in unsymmetrical charge distribution cause absorption of IR radiation. I'm repeating, only vibrations which result in unsymmetrical charge distribution causes absorption of IR radiation. In other words, we can say the vibrations should result temporary change in dipole moment of a molecule, and then only the molecule absorb that particular IR radiation. For example, if we have homopolar diatomic molecules like hydrogen, nitrogen, halides, they do not absorb IR radiation because there is no change in the dipole moment is observed. When the dipole moment is not there, even the induced dipole moment is not available, the IR radiations does not get absorbed, and we will not be able to record the IR spectra for these homopolar diatomic molecules like hydrogen, nitrogen, bromine, chlorine, etc. Another example, when we compare between carbon tetrachloride and chloroform. Here, carbon tetrachloride is a symmetrical molecule, and there is very less change in the dipole moment when the vibrations occur. Whereas chloroform is asymmetrical molecule and it has a permanent dipole moment. So in the IR spectra, chloroform absorbs strongly the IR radiation and we get good peaks or good IR spectra for the chloroform. Whereas carbon tetrachloride absorb or doesn't absorb these radiation because of the symmetrical nature or not having the dipole moment, and it is not readily observed in the IR spectrum. Now here IR spectroscopy is used, or in short, applications of IR spectroscopy. For organic chemists, the most important application is structure elucidation. It is useful for determining the structure of an organic compound. Okay. But this only IR spectra or the data from the IR spectroscopy is not enough. We need to use the data from other spectroscopic techniques like NMR, mass spectroscopy, XRD, okay, which will aid in determining the structure of a molecule. IR spectroscopy is used to study the course of a reaction. For example, if we are doing a reaction, say oxidation of alcohol, okay, it can result to formation of aldehyde or ketone, depending upon the type of alcohol, okay, primary or secondary. So, alcohols which absorb at 3300 to 3500 per centimeter, and aldehydes and ketones, they absorb in the region of 1700. So when we study the course of a reaction using IR spectroscopy, we can observe the peak for alcohol slowly get diminished, whereas a new peak for aldehyde and ketone, the product is formed around 1700 per centimeter. IR spectroscopy is commonly used to determine the purity of a sample. It is used to understand the substitution pattern in benzene or in aromatic system. For example, monosubstituted benzene ring having strong absorption and it shows two peaks in the region 750 per centimeter and 700 per centimeter. When we have di-substituted benzenes, there are three types. 1,2 di-substituted benzenes, ortho, absorb at 750 per centimeter, gives one band. 1,3 di-substituted benzene or meta di-substituted shows two band in the region 750 per centimeter and 800 per centimeter. Whereas para di-substituted, that is 1,4 di-substituted benzene, shows only one band at 850 per centimeter. Now let's have these characteristic IR frequencies for different functional groups. Okay. There are these two tables which represent the characteristic frequencies. Alkanes usually having stretching frequencies around 2800, okay, and it shows a strong absorption band. Alkenes have stretching frequencies in the region of 1600 to 1650. Alkynes having stretching frequencies of C triple bond 3 C between 2100 to 2200. Aromatic rings which are having stretching frequencies of carbon double bond carbon in the region of 1500 to 1600. Then these are a few more functional groups. Alkyl halides, alcohols typically shows stretching frequencies in the region of 3200 to 3600. Is a strong and broad peak we observe in the IR spectra. The CO stretching is also seen in the alcohols in the range of 1000 to 1200 per centimeter. Aldehydes and ketones, they are showing the CO stretching frequencies in the region of 1690 to 1725 per centimeter. And aldehyde shows a CS stretching frequency in the region of 2695 or we can say 2700 to 2800. Carboxylic acid, they are having typical stretching frequencies of carbonyl compound in the range of 1700 to 1725. And the carboxylic acid, we have OH stretching frequency, which is slightly lower than alcohol, and it is in the region of 2500 to 3000 per centimeter. So these are the few characteristics IR frequencies for different functional groups.